sort of paradoxically, whilst we are definitely physically insignificant, I've just said that the Earth is one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in a small patch of the universe, right? So we're definitely small. You can't argue with that. We're just specks of dust. But if you think about what we are, so everybody, me and you, everybody, we're just collections of atoms, right? Some of them are as old as time, pretty much, and some of them were the other ones. Everything else, other than the hydrogen in our bodies, was made in stars, right? So we're all cooked over billions of years. And we're in this pattern that can think. So suddenly, as the great Carl Sagan said, you have a means by which the universe understands and explores itself, which is us. And that sounds unlikely when you put it like that, that you can have a few things that were cooked in the hearts of stars, you stick them together in a pattern, and suddenly it has some ideas and starts writing music and arts and things. That's quite difficult to comprehend, right? But that happened here. We know that because we're sat here having a conversation. And so the question then becomes, well, on how many other worlds did that happen? And that's where I think the value can come in, because it's a reasonable guess, and it's just a guess, right? But it's reasonable. You can make the argument that there aren't any other worlds where this happened, certainly in our galaxy. So it could be that this planet, notwithstanding its physical insignificance, is the only place where anything thinks, right? For millions of light years in every direction. And suddenly, therefore, you end up considering this planet as being the most valuable place in the local universe, notwithstanding the fact that it's small. And that idea, it's not just a complete random guess, by the way. We've had a bit of a look. Astronomers have pointed radio telescopes up at the stars for a while, 50 years or more now, and heard nothing. We've seen no evidence of any civilizations out there beyond Earth. And that's a surprise. There's a reasonably plausible explanation for that, which is biology, which is that if you look at the history of life on Earth, then you see that life began pretty much as soon as it could here on Earth. We have evidence there was life 3.8 billion years ago, something like that. And the Earth's 4.5 billion years old, so pretty quick in geological time you get life. But then if you talk about advanced life, complex life, multicellular life, then there's no evidence at all back beyond a billion years. Actually, really, in the fossil record, 650 million years ago or something, you start seeing the first evidence of complex creatures. So that means that on this planet, it took over 3 billion years to go from single cell life to anything more complex than a single cell. And then another 500 million years or so to go from the multicellular things to a civilization. So it's 3.5 to 4 billion years. It's a third of the age of the universe. That is a really long time. If you say that's an unbroken chain of life on a little piece of rock in a violent universe, and that chain was not cut for 4 billion years in order to get us. And that might be a big ask, right? We live in a really violent universe. You look at the Milky Way and you look at that arc of stars across the sky, 400 billion suns. All there will be up there at best is slime. Nothing, right? And I think that's a reasonable guess. That's where I start from. I mean, I wouldn't be surprised if that's wrong. Then you go, okay, good, well, fine. But at the moment, it looks like there isn't anything else other than slime. We haven't even discovered slime, by the way, yet. We're still in the position where we've not seen anything, not even a single cell on Mars or the moons of Jupiter or somewhere like that. So at the moment, we are alone, as far as we can tell.
I just want to give you a different perspective of what I think what particle physics really means to me, particle physics and cosmology. And that's that I think it's given us a wonderful narrative, almost a creation story, if you'd like, about the universe from modern science over the last few decades. And I'd say that it deserves, in the spirit of Wade Davis's talk, to be at least put up there with these wonderful creation stories of the peoples, the high Andes and the frozen north. This is a creation story, I think, equally as wonderful. The story goes like this. We know that the universe began 13.7 billion years ago in an immensely hot, dense state, much smaller than a single atom. It began to expand about 1,000,000 billionth of a second. I think I got that right. After the Big Bang, gravity separated away from the other forces. The universe then underwent an exponential expansion called inflation. In about the first billionth of a second or so, the Higgs field kicked in, and the quarks and the gluons and the electrons that make us up got mass. The universe continued to expand and cool. After about a few minutes, there was hydrogen and helium in the universe. That's all. The universe was about 75% hydrogen, 25% helium. It still is today. It continued to expand. About 300 million years, then light began to travel through the universe. It was big enough to be transparent to light. And that's what we see in the cosmic microwave background. George Smoot described as looking at the face of God. After about 400 million years, the first stars formed, and that hydrogen, that helium, then began to cook into the heavier elements. So the elements of life, carbon and oxygen and iron, all the elements that we need to make us up, were cooked in those first generation of stars, which then run out of fuel, exploded through those elements back into the universe. They then recollapsed into another generation of stars and planets. And on some of those planets, the oxygen, which had been created in that first generation of stars, could fuse with hydrogen to form water, liquid water on the surface. On at least one, and maybe only one of those planets, primitive life evolved, which evolved over millions of years into things that walked upright and left footprints about 3.5 million years ago in the mudflats of Tanzania, and eventually left a footprint on another world and built this civilization, this wonderful picture. They turned the darkness into night, and you could see the civilization from space. As one of my great heroes, Carl Sagan, said, these are the things, and actually not only these, but I was looking around, these are the things, right? Saturn V rockets and Sputnik and DNA and literature and science. These are the things that hydrogen atoms do when given 13.7 billion years. Absolutely remarkable. And the laws of physics, right? So the right laws of physics, they're beautifully balanced. If the weak force had been a little bit different, then carbon and oxygen wouldn't be stable inside the hearts of stars, and there would be none of that in the universe. And I think that's a wonderful and significant story. 50 years ago, I couldn't have told that story because we didn't know it. It makes me really feel that civilization, which, as I say, as if you believe the scientific creation story, has emerged purely as a result of the laws of physics and a few hydrogen atoms, then I think, to me anyway, it makes me feel incredibly valuable. So that's the LHC. The LHC is certainly, when it turns on in summer, going to write the next chapter of that book. And I'm certainly looking forward with immense excitement to it being turned on.
So the first thing to say is this theory, it's called the Standard Model of Particle Physics, is a quantum theory, and it's a description of 3 of the 4 forces of nature. So other than gravity, it describes at a fundamental level everything we know about the way the universe works, at the basic level. There's electricity and magnetism, the strong nuclear force, the weak nuclear force. And it contains this thing called the Higgs mechanism. It's a unique mechanism in physics. It essentially says that less than a billionth of a second after the Big Bang, that something condensed out, if you like, into the vacuum. So that the technical word for this Higgs field is a condensate. So you can imagine almost it's similar physics to water condensing out onto a pane of glass. So a cold pane of glass, and you see liquid water appear on it. So the water vapor changes state, becomes liquid. It's very similar to that, actually, in some ways. It's a radical suggestion. And then the suggestion is that things get mass by interacting with this condensate, almost, if you like, bouncing off Higgs particles. It's slightly looser language, but essentially zigzagging through this stuff, and that's how things get mass. So it's a very odd theory. And actually, more than that, if you calculate naively the energy wrapped up in this Higgs field in every cubic meter of space, you find out that it's greater than the solar energy output in 1,000 years. So more energy than the sun outputs in 1,000 years per cubic meter. It's a very odd theory. It actually turns out that that's correct. And what I think is so that's odd in itself. We found that's a true description of nature. What I think is even more interesting is it was in there, that proposal was made for mathematical reasons by Peter Higgs and others back in the 1960s. So it was almost, I think, an observation that this is a cool, almost a trick. Maybe that's devaluing it. It's almost like a cool trick we can give masses to things, preserve the beauty or the symmetry, if you like, of these equations, if we are allowed this rather strange mechanism. So I think that it's one of the great demonstrations of the power of mathematics in physics, in theoretical physics, predicting something that's real. So this is not esoteric. This is absolutely the reason why the fundamental particles get their mass. So why an electron has mass, or why the W and Z particles that carry the weak force have mass. We now know that's correct. We don't know yet which Higgs particle it is. I mean, technically, if you're being absolutely precise, we don't actually know it. We've discovered a Higgs particle. It's a boson, definitely. A boson about 126 times the mass of the proton, give or take. So it's a boson with the right mass and some of the right properties to be a Higgs. But actually, the challenge now at CERN is to measure how this thing decays. We've seen it decay into 2 photons, for example, which is how we know it's a boson. But we want to see it decay into electrons or tau, all the different things it can decay into, and see if that matches the predictions of the basic Higgs theory, the so-called standard model. Or is it a different one? There are theories where there are 5 Higgses, for example. So could it be one of a number of Higgs particles? We don't know that yet.
I find it inconceivable there aren't other civilizations out there somewhere. The question is how far, really? Do they overlap in time, and how far do you have to go to find one? And if it's true that we're the only civilization in the Milky Way, in a sense, I think that's all that matters to us. Because I don't see any chance of civilizations crossing between galaxies. I just don't see it. You could do it. The laws of physics don't stop you from doing it. And that's just the way, one example would be the way that relativity is, even without wormholes or anything like that. Just special relativity, Einstein's theory of special relativity tells you as you go close to the speed of light, let's say you launch from the Earth, and accelerate such that at some point you're traveling, let's say 99.999999% the speed of light, because I know this number. So if you're going at that speed, then the distances between the galaxies, let's say the Andromeda galaxy, that shrinks by a factor of 7,000. It's called the gamma factor in relativity. So the distance to the Andromeda galaxy is no longer, from the point of view of the spacecraft, is no longer 2.5 million light years. It's 2.5 million light years divided by 7,000, which is still not enough, right, to get you there in any reasonable time. But you can, as you approach close to the speed of light, that factor can become arbitrarily large. According to just physics, if you could do that, you can travel between the galaxies. But you've got to travel extremely close to the speed of light in a human lifetime. The limit, by the way, in relativity, which you can't, but if you were to travel at the speed of light, then the distance shrinks to zero. The closer you get to speed of light, from the point of view of someone in the spacecraft traveling between the galaxies, the more the distance shrinks. The flip side is that time passes more slowly on the spacecraft relative to the person on the Earth, and so you can all those things. But that's just standard first year undergraduate relativity. So I wouldn't claim the laws of nature, as we understand them, stop you traveling between galaxies. But the challenge of traveling very, very, very close to the speed of light, I think it looks impossible from our perspective. Are you worried about the future of the world? Yes, definitely. And my worry, I'm also optimistic, because if we can transcend our differences, if we can work out how to organize ourselves on a planet and face global challenges together rather than in an adversarial way, then the possibilities for us are endless and wonderful and magnificent. We're at the threshold now of spreading out from the Earth, becoming a multiplanetary and ultimately an interstellar civilization. So we know how to do it. So we're at the threshold of a remarkable transformation in our fortunes. But I'm worried that just because of our internal differences as people and countries living on this one spacecraft, essentially, then we won't manage to get to that. It's within our grasp. So a magnificent future is within our grasp. And it worries me that we might not be able to grasp it.
So, one of my most illustrious forebears at Manchester University, Ernest Rutherford, the discoverer of the atomic nucleus, once said, all science is either physics or stamp collecting. Now, I don't think he meant to insult the rest of science, although he was from New Zealand, so it's possible. What he meant was that what we've done really is stamp collect there. Okay, we've discovered the particles, but unless you understand the underlying reason for that pattern, why it's built the way it is, really you've done stamp collecting, you haven't done science. Fortunately, we have probably one of the greatest scientific achievements of the 20th century that underpins that pattern. It's the Newton's laws, if you want, of particle physics. It's called the Standard Model. Beautifully simple mathematical equation. You can stick it on the front of a t-shirt, which is always the sign of elegance. This equation, though, allows you to calculate everything other than gravity that happens in the universe. So you want to know why the sky is blue, why atomic nuclei stick together. In principle, if you had a big enough computer, why DNA is the shape it is. In principle, you should be able to calculate it from that equation. But there's a problem. Each of these terms refer to some of the particles. So those W's there refer to the W's and how they stick together, these carriers of the weak force. The Z's the same. But there's an extra symbol in this equation, H. Right, H. H stands for Higgs particle. Higgs particles have not been discovered, but they're necessary. They're necessary to make that mathematics work. So all the exquisitely detailed calculations we can do with that wonderful equation wouldn't be possible without an extra bit. So it's a prediction of a new particle. What does it do? Well, we had a long time to come up with good analogies, and back in the 1980s when we wanted the money for the LHC from the UK government, Margaret Thatcher at the time said, if you guys can explain in language a politician can understand what the hell it is that you're doing, you can have the money. I want to know what this Higgs particle does. And we came up with this analogy and it seemed to work. What the Higgs does is it gives mass to the fundamental particles. And the picture is that the whole universe, and that doesn't mean just space, it means me as well and inside you, the whole universe is full of something called a Higgs field. Higgs particles, if you will. The analogy is that these people in a room are the Higgs particles. Now, when a particle moves through the universe, it can interact with these Higgs particles. But imagine someone who's not very popular moves through the room. Then everyone ignores them. They can just pass through the room very quickly, essentially at the speed of light. They're massless. And imagine someone incredibly important and popular and intelligent walks into the room. They're surrounded by people and their passage through the room is impeded. It's almost like they get heavy, they get massive. And that's exactly the way the Higgs mechanism works. The picture is that the electrons and the quarks in your body and in the universe that we see around us are heavy, in a sense, are massive, because they're surrounded by Higgs particles. They're interacting with the Higgs field. If that picture's true, then we have to discover those Higgs particles at the LHC. If it's not true, because it's quite a convoluted mechanism, although it's the simplest we've been able to think of, then whatever does the job of the Higgs particles, we know have to turn up at the LHC. So that's one of the prime reasons we've built this giant machine. I'm glad you recognise Margaret Thatcher, actually. I thought about making it more culturally relevant. So that's one thing. That's essentially a guarantee about what the LHC will find. There are many other things. You've heard many of the big problems in particle physics. One of them you heard about dark matter, dark energy. There's another issue, which is that the forces of nature, it's quite beautiful actually, seem, as you go back in time, they seem to change in strength. Well, they do change in strength. So the electromagnetic force, the force that holds us together, gets stronger as you go to higher temperatures. The strong force, the strong nuclear force, sticks nuclei together, gets weaker. And what you see in the standard model, you can calculate how these change, is the forces, the three forces other than gravity, almost seem to come together at one point. It's almost as if there was one beautiful kind of super force back at the beginning of time, but they just miss. Now, there's a theory called supersymmetry, which doubles the number of particles in the standard model, which at first sight doesn't sound like a simplification. But actually, with this theory, we find that the forces of nature do seem to unify together back at the Big Bang. Absolutely beautiful property. The model wasn't built to do that, but it seems to do it. Also, those supersymmetric particles are very strong candidates for the dark matter. So a very compelling theory. That's really mainstream physics. And if I were to put money on it, I would put money on, in a very unscientific way, that these things would also crop up at the LHC. Many other things that the LHC could discover.
When you popularise science, as you know, then there will be people who say, well, it's too important to be treated in that way. Actually, I think it's the reverse. Science is too important not to be part of popular culture. It is, as Carl Sagan always emphasised, it is absolutely the foundation of our society. We live in scientific societies. So to have a society where science is somehow divorced from the rest of culture, it seems to me to be, Sagan again emphasised, it's almost anti-democratic. It is anti-democratic because you have people who live in democracies whose lives are controlled by scientific decisions. If they know nothing about the science, then there's a democratic deficit, and you have problems because society can make decisions that are not based on reason. Obama did make a very clear statement about climate change in his victory speech, which I thought was very important. And that's an example. That's because you have a society where there are many people who don't understand that science is not a belief system and it's not a point of view. The scientists are not an interest group. I mean, politically maybe they can be when they're lobbying for funding, but essentially, science is a process. It's the process by which we understand how nature works. So if you want to ask a question about, is it true that putting carbon dioxide into the atmosphere heats the climate? There is only one way to find out. It's to get data, build models, and try and understand the data. There is no other way. You can't sit there and say, well, I'd rather it wasn't, because that would be unfortunate, have tax implications. That's contentless. So I think that's the point about, I feel quite strongly that the science, it jostles for position. Right? We live, we work in the media as well as being scientists. And you've got reality TV shows and Dancing with the Stars or whatever. And science has to compete in that arena for attention. And to, particularly amongst children as well, you've got to inspire them. They're also inspired by pop music and they're inspired by sports. They need to be inspired by science.
As Sir Peter said, I believe that we are entering, or we certainly have the possibility of entering, a new golden age of physics. The statistics speak for themselves. The increase in interest in physics across all areas of the public, but also the increase in applications to university, I think, is something that many of us thought we'd never see. And I suppose one of the reasons for that is the great success that we've had in research over the last couple of years. I'm thinking particularly of the Nobel Prizes in physics for the discovery of graphene. And of course, as Sir Peter mentioned, the Large Hadron Collider. I was asked to give a brief, I suppose, an overview of the tremendous scientific achievement that the LHC and CERN, and of course Peter Higgs's theoretical achievement back in the 1960s, what an achievement that is. I mean, you think about it, back in 1964, I think the first papers were published. Peter Higgs and colleagues predicted that we live in a condensate, so less than a billionth of a second after the universe began. Something happened, a phase transition probably, which caused the Higgs field, Higgs particles if you like, to condense out into the vacuum. The figures are remarkable. I had to check this several times. I've written it down here. The number is that if you asked a naive question, how much energy is contained in that field, the binding energy of this condensate, then per meter cubed, in every meter cubed volume of space, 10 to the 37 joules of binding energy in that condensate. If you do the simple sums, that's more than the energy output of the sun in 1,000 years per meter cubed of space, which should, given our current understanding, blow the universe to bits in a fraction of a second. It obviously doesn't. We don't know the answer to the question why. But if you think about it, it's a very bizarre prediction. It's strange. It's I think one of the best examples of Wigner's famous essay, The Unreasonable Effectiveness of Mathematics in the Physical Sciences. This is a mathematical prediction made in the 1960s, before the Standard Model was there, before we had a mature theory of the way that the strong force, the weak force, the electromagnetic force stick together. And yet that prediction has persisted all the way through to this day, to the point where over 80 countries from around the world got together and built, in many ways, the most sophisticated machine, the most sophisticated scientific experiment ever built, in many ways the most sophisticated machine that was ever built, operated it at the moment probably beyond design expectations, and discovered that prediction of nearly 50 years ago now was true. It's a tremendous scientific achievement. It's a very strange prediction. It's a very strange discovery that's going to take many, many years to understand and unravel. I've heard it described as a door that's been opened to a new world of physics. And I think that surely is correct. So a tremendous amount of work to do at CERN. But also it was a tremendous cultural triumph. It had an enormous cultural impact. And I've written down some of the headlines here. One of my favourites was The Sun, which said, "Subatomic smitten." It also underneath said, it reported in detail what Peter Higgs did on the day. And this is The Sun, this is headlines in the biggest selling national newspaper in the UK. It said, Peter celebrated by drinking a can of London Pride. And it quoted him. He only gave one quote to them. He said, "It's very nice to be right sometimes." The Daily Mail even said it was a momentous day for science, although that followed their headline on the day we turned the Large Hadron Collider on for the first time, which was, "Are we going to die next Wednesday?"
I thought it was amusing. I've got the article here from the Mail. I thought you'd be amused to see. There's actually a serious point to this, actually, which I'll make afterwards. But first, you can laugh at this journalism. They said that there were two potential problems with the LHC, the problems it might cause for humanity. And this is word for word. They said, for maybe a month, this is the least problematic scenario. For maybe a month, there will be no sign that life is about to come to an abrupt and nasty end for all living things on Earth. Earthquakes will start unexpectedly, alerting geologists that something terrible is amiss. After a few days, these seismic disturbances will reach catastrophic proportions. Cities will be leveled, the oceans will rise and wash in a series of mega tsunamis that will attack the world's coast, killing millions. The fact that the earthquakes are striking at random will be proof that something devastating is afoot. The end will come in a disaster on a biblical scale. The earth will start to crack up, molten lava will wash over the land and the seas will start to boil. Mega hurricanes will level buildings and forests the world over. Mountains will crumble, the earth's crust will continue to disintegrate. The fabric of the planet itself will start to disappear, and from space our blue and white home will vanish down a plug hole in a flash of light. You could look at this and say, well, at least science, particle physics, was on the front page.
So one of our theories is that space and time, for that matter, so I should say back in 1905, Einstein realised that space and time are not separate, but they're woven together into something that's often called the fabric of the universe, or more technically space-time. But we now suspect, or at least we have a theory, that space-time emerges from something deeper, which is just basically quantum entanglement. So we think that there is a description of our universe which is just bits of information, basically, or qubits to be more technical, quantum bits of information that are entangled together into some sort of network. So space and time don't exist in that network, and then space and time emerge from that deeper theory. This is cutting-edge physics, but it's one of the pictures that we have for what space and time might be.
Yeah, in a technical sense, what you do, you ask the question, which is all that quantum mechanics tells you, really, is that I have a particle here at one point, and I want to know the probability of it being over here at the next point. What do you do? Well, technically what you do is you add up a quantity, well, the action actually, but it doesn't matter what it is. You basically consider the particle moving every possible path from A to B. And Feynman's approach is to do that mathematically. So add up a set of quantities for each possible way something can get from one place to the other, and you get the probability out in the end that it will actually be in the vicinity of that point at some future time. So it's a statement of sort of technical fact in a way about how you do calculations in quantum theory. I'm a member, I think, of the shut up and calculate school of physics, where quantum mechanics works. It's the way we design transistors, etc. It is our best explanation of everything in the universe other than gravity. The problem with the theory, in an interpretive sense, is that you ask the question, well, so we accept the fact that atoms behave in a strange way. And also the theory does tell you how classical behaviour, so the behaviour of cups and things and people, how that emerges from the theory. But you still have this problem that when you try to interpret it as a theory of big things, then you get these Schrodinger's cat type problems where things are indeed, everything that can happen is happening. Cats can be alive and dead, people can be in an infinite number of places at once. And so it's how you interpret that. I think that the problem really is it's a probabilistic theory. So it's telling you about the probability that things will happen. And if you think about it, how do you interpret that? What does it mean to say, well, there's a 50% chance it's going to be here? Well, you might say, well, no, but it is there, isn't it? Well, no, it isn't. There's a 50% chance it's going to be there. That's how the theory works.
Quantum mechanics grew out of an attempt to understand some curious experimental findings, which actually at the time weren't considered to be so problematic. There were questions about the colour of light or the nature of light emitted by atoms. So very famously, for example, sodium vapour. If you remember old sodium vapour streetlights, and they glow kind of yellowy orange, and the question was, why? So there's a colour of light from atoms. The origin of quantum mechanics, though, probably can be traced to Planck's explanation of the way that hot objects radiate. So 1900, the late 1890s, 1900, there was a problem with the calculation of how a hot object radiates in terms of the wavelengths of light that it emits and the calculation. Essentially, the calculations of the wavelength of the light from hot things were just wrong. And in 1900, Max Planck made a revolutionary proposal. I've read in some biographies of Planck that it was essentially a leap of genius, almost inexplicable. But he famously came up with the idea that a hot object only emits light in little packets, which subsequently we came to know as photons following Einstein, but that was much later. So it's this idea that a glowing thing doesn't just emit light at all wavelengths and radiate all sorts of light, but it somehow, for some reason that was not known to him at the time, emits wavelengths, radiation in little packets. And so that was a huge leap. And actually, he didn't really at the time think that he thought it was a calculational device. But what's important is that the fundamental constant of nature that we associate with quantum mechanics, now known as Planck's constant, appears in the calculation. And so very specifically, Planck found he was able to describe the experimental data if he assumed that light is emitted in little packets, and the relationship of the energy of the little packet, the photon as we would now call it, to the frequency of the light is E equals hf, where f is the frequency of the light, E is the energy of the packet, and h is this new constant of nature that we now know as Planck's constant. So I would say that's the beginning of modern quantum mechanics.
Yeah, basically these maintenance shutdowns are very difficult to do on the LHC because it's cold, so it runs at minus 271 degrees or so, very close to absolute zero. So it takes a month or so to warm the thing up and a month to cool it down. And obviously the things, you can have problems when you warm things up and cool things down. So you try to not do maintenance on the machine. So you have long maintenance things. So it's a planned maintenance, which has already been pushed back because it's running so well. I mean, it's running beyond anybody's expectations, which is a tremendous achievement for this thing. Which you must remember is the most complicated machine by some measure that we've ever built in history. And the fact that it works better than expected and has already made this discovery, which is really one of the key reasons that the machine was built, I think is remarkable.
This is the Large Hadron Collider. It's 27 kilometers in circumference. It's the biggest scientific experiment ever attempted. Over 10,000 physicists and engineers from 85 countries around the world have come together over several decades to build this machine. What we do is we accelerate protons, so hydrogen nuclei, around at 99.999999% the speed of light. Right, at that speed, they go around that 27 kilometers 11,000 times a second. And we collide them with another beam of protons going in the opposite direction. We collide them inside giant detectors. They're essentially digital cameras. And this is the one that I work on, Atlas. You get some sense of the size. You can just see these EU standard size people underneath. You get some sense of the size. 44 meters wide, 22 meters in diameter, 7,000 tons. And we recreate the conditions that were present less than a billionth of a second after the universe began. Up to 600 million times a second inside that detector. Immense numbers. And if you see those metal bits there, those are huge magnets that bend electrically charged particles so we can measure how fast they're traveling. This is a picture about a year ago. Those magnets are in there, and again, an EU standard size real person. So you get some sense of the scale. And it's in there those mini Big Bangs will be created sometime in the summer this year. And actually this morning I got an email saying that we've just finished today building the last piece of Atlas. So as of today, it's finished. I'd like to say that I planned that for Ted, but I didn't. So you might be asking, why? Why create the conditions that were present less than a billionth of a second after the universe began? Well, particle physicists are nothing if not ambitious. And the aim of particle physics is to understand what everything's made of and how everything sticks together. And by everything, I mean, of course, me and you, the Earth, the Sun, the 100 billion suns in our galaxy, and the 100 billion galaxies in the observable universe. Absolutely everything. And you might say, well, okay, but why not just look at it? If you want to know what I'm made of, let's look at me. Well, we found that as you look back in time, the universe gets hotter and hotter, denser and denser, and simpler and simpler. Now, there's no real reason that I'm aware of for that, but that seems to be the case. So way back in the early times of the universe, we believe it was very simple and understandable. All this complexity, all the way to these wonderful things, human brains, are a property of an old and cold and complicated universe. Back at the start, in the first billionth of a second, we believe, or we've observed, it was very simple. It's almost like, imagine a snowflake in your hand and you look at it and it's an incredibly complicated, beautiful object. But as you heat it up, it'll melt into a pool of water and you would be able to see that actually it was just made of H2O, water. It's in that same sense that we look back in time to understand what the universe is made of. And as of today, it's made of these things. Just 12 particles of matter stuck together by 4 forces of nature. The quarks, these pink things, are the things that make up protons and neutrons, that make up the atomic nuclei in your body. The electron, the thing that goes around the atomic nucleus, held around in orbit, by the way, by the electromagnetic force that's carried by this thing, the photon. The quarks are stuck together by other things called gluons. And these guys here, the weak nuclear force, probably the least familiar, but without it, the sun wouldn't shine. And when the sun shines, you get copious quantities of these things called neutrinos pouring out. Actually, if you just look at your thumbnail, about a square centimetre, there are something like 60 billion neutrinos per second from the sun passing through every square centimetre of your body. But you don't feel them because the weak force is correctly named. Very short range and very weak, so they just fly through you. And these particles have been discovered over the last century, pretty much. The first one, the electron, was discovered in 1897. And the last one, this thing called the tau neutrino. So this thing was discovered in the year 2000, so it's a relatively recent picture. One of the wonderful things, actually, I find, is that we've discovered any of them when you realize how tiny they are. The step in size from the entire observable universe. So 100 billion galaxies, 13.7 billion light years away. The step in size from that to Monterey, actually, is about the same as from Monterey to these things. Absolutely exquisitely minute, and yet we've discovered pretty much the full set.
So in our solar system, primarily, although it is possible, I should say, that with the James Webb Space Telescope and other instruments that are coming online now, that it's possible we could detect biosignatures in the atmospheres of planets around distant stars. But that's at the edge of our capability at the moment. So at the moment we're talking about, of course, the missions to Mars. Not yet quite designed to detect life, but to check if the conditions were present on Mars that may support life. I think it's fair to say we're pretty sure that the conditions on Mars 4 billion years ago, let's say, were very similar to the conditions that led to the origin of life on Earth. And so we've got the Perseverance rover now, which is taking samples as part of the Mars Sample Return mission, which hopefully, although the timeline is by no means clear, but hopefully those samples will return to Earth at some point, let's say in the next decade or so, with luck. That's because we suspect that there may be evidence that life existed or may still exist on Mars, because we're pretty sure that there were oceans, or at least lakes and rivers on Mars for a reasonable amount of time, around 4 billion years ago. And we know that there's a high water content in the soil. I think we suspect there may be pockets of water below the surface. So it's possible life may still exist on Mars. So that's an open question. As we speak, there are 2 missions in flight to Jupiter, to the Jovian system, in particular focused on Europa, which is Jupiter's moon, which is famously, I think, one of the prime candidates for life beyond Earth. Because it has an ocean, a saltwater ocean, it has active geology, and it seems as if that ocean has been there for a very long time. So the 2 missions that are on the way are Europa Clipper, which is the NASA mission, and JUICE, which is a European mission, which are both really focused at not looking for life specifically. They're not equipped to do that, but to see if the conditions are right in preparation, hopefully, for a future mission.
There are a lot of things about the universe that I find it almost impossible to imagine. Well, actually impossible to imagine. One's just the size and scale of it. I mean, in the piece of the universe we can see, there are something like, roughly, 2 trillion galaxies. We haven't counted them all, but that's an estimate based on surveys of the local universe. 2 trillion. 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy, and there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it. It is impossible to visualize the scale of the universe.
We live in a society, as the great physicist and communicator Carl Sagan always emphasized, a society that is entirely based on science. It is based on technology and engineering. All the great important decisions that our democracy will be forced to take in the next decades and onwards into the 21st century are based on science. They're based on the scientific method. They're based on an understanding of what reason and reaching conclusions based on evidence is. And if the presentation of science is a Frankenstein presentation of science, a misrepresentation of what we do, a complete mis-selling of the wonder of exploration, then we have a problem in our democracies. And it's the same problem that we have if we don't have an educated population, a population that is educated in STEM subjects, as Sir Peter emphasised. So For a democracy, a modern scientific democracy, to function correctly, then you need as many citizens as possible to at least have an understanding of the scientific method, if not the facts. You don't need to know the mass of the Higgs boson, but you need to know how we go about answering questions such as, how did the fundamental particles acquire mass in the universe? It's a scientific method that matters. So it's not acceptable to do that. It's not acceptable to claim, and I'm going to quote here, and I'll tell you who wrote this later. It's not acceptable to claim that homeopathic care is enormously valued by thousands of people, and it ought to be available where a doctor and patient believe that a homeopathic treatment may be a benefit to the patient. Jeremy Hunt said that. That's a statement to evidence-based medicine, what Nigel Lawson is to polar ice caps. It's not accuracy. It's not acceptable to attack the claims of science. I'm thinking particularly about climate change here, because you don't like the economic impact of the problem. It's not acceptable to not understand what the difference is between data and modelling and political statements about what you do about the consequences of that data and modelling. I'm always reminded of my friend Dara O'Brien, who talks in wonderful terms about these ideas. He says that there's no such thing as alternative medicine. Right? There's medicine, which has been shown to work, and there's potpourri. I noticed the Royal Academy of Engineering report actually earlier, I think it was earlier this week or maybe last week, which made quite salutary reading for the future of our economy if we don't do if we don't invest in STEM subjects, if we don't change this attitude that is prevalent in many parts of society, that science is just one, or scientists and engineers are just one set of interest groups amongst a wider population. The Royal Academy of Engineering said that we need, or found that we need 100,000 STEM graduates per year into the economy in order to stand still. 1 million, of order 1 million by 2020, and around 500,000 technicians. Now, those are big numbers. Currently, we graduate around 90,000 STEM graduates per year, but that includes foreign students, and around 25% of those don't remain in the STEM industries. So you can see there's a shortfall into the economy to stand still of something like, maybe 30,000 STEM graduates per year. So my personal view is that, as Sir Peter said, we've turned the corner in some sense. We, as a community, have, in a sense, done our job. We've convinced young people that physics, that science and engineering are things that they should be interested in and are worthwhile doing. My challenge to government now is, what are you going to do about that? Because we're finding it difficult to educate them all. I know at Manchester we have entry requirements now in physics, I think of A star, which is to be applauded. But in a sense, it seems to me it's a market failure, because there are more people that want to come and do physics at Manchester than we can take, because we don't have the infrastructure, we don't have the lab space, we don't have the lecture theatres and the staff to teach those people that are vital for our economy. And don't say we can't afford it. There was another interesting report that came out last week, I think, for the OECD. It was looking at the impact of tertiary education on economies. It's a very detailed and careful report. It found that the net return on public investment in the UK on a person who goes through tertiary education, so not STEM necessarily, but just tertiary education, is around $70,000 over their lifetime. So after you subtract out all the loss of tax income while they're at university or while they're in tertiary education, and then all the cost of their education, you still find that $70,000 on the average comes into the economy over the lifetime. You multiply that by 1 million STEM graduates, there's $70 billion for those extra 1 million graduates we want over the next 10 years. There are other social consequences. It's a fascinating report. Life expectancy is 8 years longer for males who go through tertiary education than males that don't. 27% more tertiary educated people vote than non-tertiary educated people. So you increase the participation in the democracy by an incalculable amount. Over half the GDP growth in all OECD countries over the past decade came from tertiary education, tertiary educated people. Half of GDP growth. That sector of the UK economy grew last year, even though we're in recession. So where would this investment come from? I'm talking about the investment to build our capacity to educate more STEM graduates. Well, there's a very interesting campaign that you're going to hear a lot more of. Imran Khan, who's set over there, is going to run the campaign, also James Dyson. The idea is to look at the sale of the 4G spectrum, which is going to raise at least $1 billion, $1.5 billion, possibly more than that. I know Ed Bowles recently suggested that should go into a stamp duty holiday. What the suggestion of this campaign is that money should go into science infrastructure. I noticed that the Lib Dem pledge to increase the science budget year on year by 3% a year is very important. That's what we should be trying to get all parties to commit to. 3% increases year on year in the science budget as a whole. But that infrastructure money from the sale of the 4G spectrum could at least provide us with the capacity to educate all these STEM graduates that we need. And I just want to finish by saying this isn't new. The need of an economy for STEM graduates, for physics graduates, and all the way through engineering, mathematics, and the physical sciences isn't new. I was at the Royal Institution a few weeks ago, and I was shown the prospectus from the Royal Institution, the founding document. Essentially, it's the document that they were giving to potential donors to explain why an institution which promoted science and engineering was necessary. In 1799, it was primarily written by Joseph Banks. And I found this paragraph in it, which is remarkably modern. All you have to do in it is, you've got to remember at the time, it was the rich that held the power in Britain. So there's a word in here about the rich. It means really the politically powerful, the influential opinion formers. But it says this right at the end of the prospectus. But in estimating the probable usefulness of this institution, we must not forget the public advantages that will be derived from the general diffusion of a spirit of experimental investigation and improvement among the higher ranks of society. When the rich shall take pleasure in contemplating and encouraging such mechanical improvements as are really useful, good taste with its inseparable companion good morals will revive, rational economy will become fashionable, industry and ingenuity will be honoured and rewarded, and the pursuits of all the various classes of society will then tend to promote the public prosperity. I mean, I think that with a slight modification from the rich to the influential and powerful should be presented to David Cameron and every future Prime Minister, because it's as true today as it is to now. And remember, at the time in 1799, Britain was in danger of being extinguished. We're in a crisis greater than the one we are now. We could have ceased to be as a nation if we hadn't won in 1812. The economy was in a mess, and these people felt that engineering and science was the way to secure the future of the then empire and the economy in general. And I think that was echoed by, I want to finish with a quote that I really think is very powerful. It was given by Humphrey Davy not long after that. When asked, why do you want to do this? Why do you want to continue to explore? We're talking about the early part of the 19th century now. The common refrain, surely we know enough. We don't need to build an LHC. We don't need to go and do medical research. We know enough now. Well, it's nonsense. Davy knew it. And he said, in response to that charge, nothing is more fatal to the progress of the human mind than to presume that our views of science are ultimate, that our triumphs are complete, that there are no mysteries in nature, and there are no new worlds to conquer.